Hello friends, in this video I am going to solve exercise question from book Topics in Algebra. Question is, if Nm are normal subgroups of G, prove that Nm over M, this quotient group, is isomorphic to the quotient group N over N intersection M. So proof, here G is a group and M and N are normal subgroups in group G. Then we have Nm is a subgroup of G and also M is a normal subgroup of Nm and N intersection M is normal subgroup of N. I have proved this result in earlier videos. You can see proof from there. Now, as M is normal subgroup of Nm and N intersection M is normal subgroup of N, Nm over M and N over N intersection M are well defined, that is, these both are quotient groups. Now, define a map, say phi, from N to Nm over M such that phi of N is equal to Nm. Now, firstly we will show that this map phi is well defined. For this, consider any two elements, say N1 and N2 in subgroup N, such that N1 is equal to N2. Then as N1 is equal to N2, we have coset N1M will be equal to coset N2M. Now N1M is phi of N1 and N2M is phi of N2. Therefore, this map phi is well defined. Next, to show that phi is onto, consider any element, say xm in the quotient group Nm over M. Now, for this coset xm in Nm over M, this xm will be equal to Nm M for x equal to Nm in subgroup Nm. Now, note that Nm M will be equal to Nm since this M is an element of subgroup M. So, these two cosets are same. Now, for N in subgroup N, we have phi of N will be equal to, by definition, this Nm coset, and which is again equal to coset Nmm, and which is equal to coset xm, which is any element of Nm over M. So here we get, for any arbitrary element xm in quotient group Nm over M, there exists an element, say N in subgroup N, such that phi of N is equal to coset xm in this quotient group, and thus the map phi is onto. Next, to prove phi is a homomorphism, consider any two elements, say N1 and N2 in subgroup N. Then phi of N1 N2 will be equal to N1 N2 M from definition of phi. Now, as M is a normal subgroup of group G, N1 N2 M will be equal to N1 M N2 M, and N1 M is phi of N1 and N2 M is phi of N2. So we get phi of N1 N2 is equal to phi of N1 phi of N2, and therefore phi is a homomorphism. Thus our map phi defined here is a well defined map which is an onto homomorphism. Next, to prove that kernel of this homomorphism phi is set M intersection N. So consider kernel phi, that will be set of all those elements N in subgroup N, such that phi of N is equal to M, that is kernel phi is set of all those elements N in N which get mapped to the identity element of Nm over M. And identity element of Nm over M is subgroup M itself. So in the next step, we can write this set as kernel phi is set of all those elements n in subgroup n such that Nm is same as M, since phi of n is Nm. Now, therefore we have kernel phi is equal to set of all those elements n in subgroup n such that n is also an element of subgroup M. Since this condition holds, so we must have n will be an element of subgroup M. And therefore kernel phi is set of all those elements which are in both subgroup n and subgroup M, and therefore kernel phi will be equal to M intersection n. Then, by first isomorphism theorem, which states that let phi from group G to group G dash be homomorphism of groups, then G upon kernel phi, this quotient group will be isomorphic to image phi. We have n upon kernel phi will be isomorphic to Nm upon M. Note that here Nm upon M is image of phi, and since phi is onto, image will be whole quotient group Nm over M. Now in the next step, replacing this kernel phi by M intersection n, we get n upon M intersection n is isomorphic to Nm upon M, and this proves our result.